Welcome back to Chem Talk. I'm excited for today's deep dive
Me too.
because we're going even deeper into the periodic table
Yeah,
to explore a really cool concept called electron affinity.
definitely.
It's episode 6-7, Periodic Trends. Electron affinity.
Yeah.
So get your periodic tables ready
Yeah, you're going to want them.
because we're about to find out just how much atoms love to snag those extra electrons
It's kind of
and why that matters.
like when you try to cram one more thing into an overpacked suitcase.
Oh, I hate when that happens.
You have to sit on it to get it to close, right?
Yeah, exactly. And even then, sometimes the zipper just bursts open.
Totally, and it takes a ton of energy to make it work.
Right.
Well, it's kind of the same idea with atoms. Adding or removing electrons can create this sort of energy tension too.
So are you saying atoms can get stressed out?
Haha, in a way, yeah. So electron affinity is all about measuring that energy change.
Okay, I'm intrigued.
So electron affinity is basically the energy change that happens when a neutral atom in a gaseous state gains an electron.
Gotcha. Why gaseous state, though?
Good question. It's the easiest way to isolate and measure the energy change without other factors messing things up.
Makes sense. So we're talking about atoms in their purest form.
Exactly. Now here's the thing. Electron affinity is usually a negative value.
Negative. So like the atom is losing energy?
It's actually releasing energy.
Oh, okay.
And in chemistry, when energy is released, that's represented by a negative number.
Huh. That's interesting.
Yeah, so the more negative the electron affinity, the more energy is released when the atom gains an electron.
So a really negative electron affinity means the atom is like, yes, give me that electron.
Pretty much. It's
Right.
like finding the perfect parking spot right when you arrive.
And are there any elements that are like the parking spot ninjas of the periodic table?
Absolutely. The halogens in group 17,
Ooh, those guys, they're always up to something.
they have the most negative electron affinities, which means they really, really want to gain that extra electron.
Guy, though, what makes them so special?
Well, remember those noble gases we talked about?
Yeah, the ones on the far right that are like super stable.
Exactly. They have a full outermost electron shell, and that makes them super chill and unreactive.
Ah, I see where you're going with this.
The halogens are just one electron away from having that same stable electron configuration.
So by snagging one extra electron, a halogen can be like, boom, I'm basically a noble gas now.
You got it. And that makes gaining that electron super energetically favorable.
So it's all about achieving that ultimate Zen-like stability.
Pretty much. And this whole electron affinity thing isn't just limited to the halogens.
Right, there are trends across the entire periodic table, right?
Exactly. Generally speaking, electron affinity increases or becomes more negative as we move from left to right across a period.
So atoms on the right side are more eager to grab electrons than those on the left.
You got it. And it all comes down to something called effective nuclear charge.
Ooh, fancy term. Breakdown, please.
Basically, it's how strongly the nucleus pulls on those outer electrons.
Okay.
As we move across a period, the number of protons in the nucleus increases.
More protons, more positive charge, right?
Exactly. And that means a stronger pull on those negatively charged electrons.
So it's like adding more magnets to attract those electrons.
Perfect analogy. So the stronger the pull, the more those atoms want to gain an electron.
Gotcha. What about going down a group? Does electron affinity change as we move down the columns?
It does. Electron affinity generally decreases or becomes less negative as we go down a group.
Why is that?
Think about it. As we go down a group, those outermost electrons are further and further away from the nucleus.
Ah, so the nucleus has less of a grip on them.
Exactly. They're experiencing a weaker pull, so they're not as eager to attract an additional electron.
So it's like the nucleus is trying to hold on, but those distant electrons are like, nah, we're good out here.
Haha. Yeah, kind of. They're a bit more independent.
But you mentioned exceptions earlier.
Oh, yeah. Can't forget those.
What's the deal with those?
Well, sometimes the trends don't perfectly hold up.
So it's not as simple as just looking at the periodic table.
Right. Sometimes an element might have a lower electron affinity than expected.
Why would that happen?
It could be due to its electron configuration or other factors.
So there's more to the story than just position on the periodic table.
Exactly. Each element has its own unique quirks.
This is making me think about how electron affinity actually plays out in the real world.
Oh, it definitely does.
So why should our listeners, especially those in 10th grade chemistry class, really care about this concept?
Well, electron affinity is a key to understanding chemical reactivity.
Reactivity.
Yep. Elements with high electron affinities, like our halogen friends.
Right. They love those electrons.
Exactly. They're more likely to gain electrons during chemical reactions and form negative ions.
Ions. those charged particles that are always up to something.
And knowing about electron affinity helps us predict what kinds of ions elements will form.
So it's not just about atoms in isolation. It's about how they interact with each other.
Exactly. Electron affinity gives us clues about how elements bond together and what kinds of compounds they form.
So it's like a sneak peek into the world of chemical reactions.
Exactly. The more you understand electron affinity, the better you'll be able to predict and explain how elements behave.
This is blowing my mind. I never thought about the periodic table this way before.
It's pretty cool, right?
So to wrap things up, electron affinity is all about how much an atom wants to gain an electron.
Right.
Halogens are like the electron magnets of the periodic table because they're one electron away from that perfect noble gas stability.
Exactly.
And there are these general trends, but also some interesting exceptions that keep things exciting.
Chemistry is full of surprises.
So much to learn. Huge thanks to you for breaking this down.
My pleasure.
And of course, a massive shout out to the Geeky Gamer Science teacher for making Chem Talk possible.